Okay, this is a pre-Unit 2 review of all the material you hopefully learned in IB Chem 1. If you have any questions about any of this, please just make an appointment to come and see me. You'll take a pre-quiz the first day of the unit to make sure that you're on track, and then after that, you'll be responsible for this material. Okay, so first let's do a quick review of isotopes. They're atoms of an element that differ in the number of neutrons and therefore in their atomic masses. The general form for isotopic notation is AXZ. A in the upper left-hand corner is the mass number, which is the protons plus the neutrons. Z is the atomic number, protons. X is just the element symbol, whatever that might be. Very frequently you see that Z is left off, and that's because you could simply look it up on the periodic table to find the atomic number. Okay, so you'll see here there's a couple different ways of writing it. When we write argon 40 like that, what we mean is that 40 is the mass number. Okay, it has to be because argon's atomic number is 18. So what I'd like you to do right now is pause this and try to figure out the numbers of protons, neutrons, and electrons in each of these isotopes. Note that bromine is actually bromide because it's an ion. So pause and try these. Okay, check your work. Hopefully you got all of these right. Now notice that since bromide has a negative charge, that means it's gained an electron, since electrons are negatively charged. Okay, now hopefully you remember how to calculate average atomic mass. Remember that if we have 3 different isotopes, for example, like we do here with silicon, we can't just say 28 plus 29 plus 30 divided by 3. And the reason is that they're not equally abundant. Okay, silicon 28 is far more abundant than the other isotopes. It would be like if you had a room with 100 people in it and 99 of them weighed 200 pounds and 1 of them weighed 100 pounds. You certainly couldn't say that the average mass of the people in that room was 150 pounds, right? So this is similar. All right, so here's an example. First of all, when you calculate average atomic mass, you take the mass times the percent plus the mass times the percent plus the mass times the percent for as many isotopes as you have, and then divide that by 100. Alternately, you can just convert the percentages into decimal form and not divide by 100. Okay, so here would be the work for this problem. Okay, and you would get an average of 28.09 atomic mass units, which is the same as the periodic table. So there's another way to approach these problems, and this is honestly what you're much more likely to be asked by IB. They wouldn't ask you to do the previous problem because you can just get the answer right off the periodic table. So here's an example of another kind of problem. Chlorine has 2 isotopes, chlorine 35 and 37, and the average is 35.45. So we'd want to determine the relative abundances of each isotope. So we have 2 things we need to find here. The abundance of chlorine 35 and the abundance of chlorine 37. So we have to ask ourselves, what do we know about their relationship? So we know that these are the only 2 isotopes, so we should be able to figure out what the percentages should add up to. Take a minute and see if you can solve this problem, and then we'll go over it. Okay. There's 2 ways you could have set this up. You want to set it equal to the average, 35.45. Now, if we say that X is equal to the abundance of chlorine 35, then the abundance of chlorine 37 must be 100 minus X, right? Because the percentages have to add up to 100. If you were to set it up this way, you would find that X was equal to 77.5, so the percent of chlorine 35 was 77.5%, and the percent of chlorine 37 was 22.5%. You could have treated the percentages as decimals from the start, in which case it would be 37 times 1 minus X, because the percentages as a decimal would add up to 1 instead of 100. And then you would get that X is 0.775, so 77.5%. All right, quick review of electron configurations. This is one of those things that you just kind of have to see again. Remember that when we write electron configurations, the whole purpose of doing that is to show which orbitals each of the electrons in an atom is in. Okay, so if we are going to start always at the very beginning, the first electrons are always going to go in the 1s orbital. Okay, The 1 tells me which energy level those electrons are living in, and the S tells me the shape of the orbital. So in this case, those first 2 electrons are going to go in the first energy level, S orbital. Okay? We're going to keep going through each of the rows until we get to the element. So for example, if we were going to find the electron configuration for neon, I'd start at the beginning, and I'd say 1s2, because the first 2 electrons will go in the 1s orbital. I'd go to the next row and say 2s2, because the next 2 electrons will go into the 2s orbital. And then I'd go across to 2p, and I see that there's 6 boxes in 2p. So the next 6 electrons will go in the 2p orbitals, so I would say 2p6. Now, the s, p, and d orbitals are the only ones you really need to know. We do have f orbitals as well, but we're not going to worry about those when we do electron configurations. I think a good way to remember their shapes is that the s is a sphere. I think the p orbital is kind of shaped like a peanut. And there's 3 p orbitals on the x, y, and z axes. You can sort of see all 3 there. And I think the d orbital looks kind of like a diaper, but it also looks like a butterfly, but in chemistry we're just going to call them butterflies because butterfly doesn't start with D. And these are basically just the shapes of the probability distribution. So we'll talk a little bit about what that means. So basically an orbital is just where electrons tend to be found. Each orbital has a defined energy state for a given environment and can hold 2 electrons of opposite spins. So we just talked about how 2p can hold 6 electrons. So the 2p sublevel can hold 6 electrons. So that must mean that there are 3 2p orbitals. 2px, 2py, and 2pz. Now, it's important to remember that electrons move randomly in orbitals. They're not going in a fixed path. The area of the orbital is where they are 99% of the time. It is theoretically possible that an electron that's assigned to a particular orbital could be outside the orbital, but it's very, very unlikely. Now, electrons fill orbitals based on energy. So they're going to fill the lowest energy orbitals first. So the 1s orbital will always be filled first. That's because lower energy orbitals are more stable. And that's sort of a general concept you need to know, is that lower energy is more stable. Now, one thing that confuses people, if you look back to the periodic table, we notice that right after 4s, where we would think it would be 4d, we actually fill 3d orbitals, okay? And the reason for that is that 4s and 3d are very close in energy, but when they're empty, the 4s orbitals are slightly lower in energy than the 3d orbitals. After they're full, however, the 4s orbitals are destabilized enough that they're slightly higher in energy than 3d. Okay, so that means that if we were to lose electrons from an atom, they would lose the 4s electrons before the 3d. Okay, so I want you to practice writing some electron configurations. If you've forgotten how to do this completely, here's one example for sodium. You can also look in your textbook and see the quick review there. That would be in chapter 2 of your textbook, topic 2. So 2.2 in your textbook. Okay, so pause this and try these electron configurations, and then we'll go over them. Okay, check your work. Now, I gave you the shorthand configuration for nickel. Hopefully you remember how to do shorthand. As you can see, the nickel configuration is really long, so rather than spending all the time to write that whole thing, what we're going to do is put the previous noble gas in brackets. So what that means is the electron configuration of argon, which is 1s2, 2s2, 2p6, 3s2, 3p6, followed by the outer electrons after that, so 4s2 and 3d8. Now, many people will write them in the first way that nickel is written, 4s2 and then 3d8. However, you'll also see that some people write 3d8 and then 4s2. Now, the reason to write it the first way is that that's the order that they fill, but the reason to write them in the second way is that once they're full, the 4s shell is outside the 3d shell. And so that second configuration accurately reflects that. But typically both are accepted by IB. Both will be accepted by me. However, you'll usually see IB used the second way. Okay, quick review of terms and trends from Chem 1. Okay, hopefully you remember atomic radius, ionization energy, and electronegativity. So atomic radius is, it's just the radius of an atom, but the way that we typically measure this is that we look at two atoms bonded together, and the atomic radius is defined as half the distance between two neighboring nuclei. The first ionization energy, and we'll talk in class about second and third, is the minimum amount of energy required to remove an electron from a neutral atom in the gas phase. And that gas phase part is important. And electronegativity is the relative attraction that an atom has for a shared pair of electrons in a covalent bond. These are relative to fluorine, which has the highest electronegativity, and that's set at 4, and all others are relative towards that. Ionization energy, in contrast, is typically measured in kilojoules per mole of an atom. There's a couple forces that affect periodic trends, and these are kind of intuitive, right? Electrons are constantly subjected to two opposing forces. They're attracted by the positive charge in the nucleus, and they're repelled by other electrons. Okay, so when we look at periodic trends, we're looking at the effective nuclear charge and the electron-electron repulsion. And basically, atomic radius can explain ionization energy and electronegativity, and we'll talk about why that is in class a little bit more. Okay, so atomic radius, hopefully you remember the trends. If you were in my class, you learned about the snowman. It increases down a group and decreases across a period. As you go across a period, you might think that atomic radius increases because we're adding more electrons. But in fact, across a period, it decreases. And this is because we're increasing the charge in the nucleus, but we're not increasing the number of occupied energy levels. So what that means is that the nucleus is pulling the outer energy level in closer as you go across. Down a group, atomic radius increases, and that's just because we have more occupied principal energy levels, so we have a larger radius. First ionization energy, as you go across a period, increases. And again, this is going to be because of the nuclear charge. So again, we're increasing the effective nuclear charge, but there's no increase in the number of energy levels. So the nucleus has a greater attraction for the valence electrons, and therefore it's going to take more energy to remove them. Down a group, the ionization energy decreases, and that's because of what's called the shielding effect. The core electrons block the pull of the nucleus from the valence electrons, so it requires less energy to remove the valence electrons. Electronegativity follows the same basic trend as ionization energy and very similar explanations. Again, increase in nuclear charge but no increase in energy levels across a period. So that means that the nucleus is going to be able to have a greater attraction for electrons in a bonding pair. And down a group decreases because the shielding effect blocks the pull of the nucleus from attracting electrons. Now, one common issue with periodic trends is explaining them. So we've just gone through all the explanations, but one command term that you'll see on IB tests is the term explain. And this means to give a detailed account of causes, reasons, or mechanisms. So sometimes you might be asked to explain why atomic radius decreases across a period. This is an actual explanation that I have seen before. Atomic radius decreases across a period because sodium has a larger radius than fluorine. Although it really would be, chlorine would be a better example here. Now, that's like saying atomic radius decreases across a period because it decreases. So here's a better explanation. Atomic radius decreases across a period because as the nuclear charge increases, but number of energy levels remains the same, the nucleus has a greater pull on the valence shell electrons. Okay, so try the practice that's on Blackboard. The key is up there as well. And make sure that you have this stuff down. If you need help, please come and see me. That's no trouble at all. And then we will move on.